Welcome to the deep dive. So today we're looking into something called astrometric microlensing.
That's right.
We first really saw light bending around, say, the sun during those eclipses, like way back in 1919 and again in 73.
Yeah, those were landmark observations. Confirmed Einstein's predictions.
And then the Hipparcos mission, that was 97, right? It sort of mapped that bending effect across the sky.
Exactly. It gave us a much broader picture.
Well, it turns out that this really subtle bending of starlight, it can tell us some amazing things about the universe.
Absolutely fundamental things, actually.
And for everyone listening who wants to get up to speed on complex stuff quickly, this is, I think, a great topic. It shows how tiny, tiny effects can lead to pretty big discoveries.
It really does. We're going to dig into how it works, why it's so significant right now in astronomy. It's a perfect case study.
Okay, so where did the idea even start? It wasn't immediate, right?
Yeah. No, not at all. I mean, the theoretical basis was there. Eddington, back in 1920, he actually suggested a nearby star could act as a lens, maybe create two images of a background star.
Okay, so the idea was floated early on.
But then Einstein himself, in 1936, he sort of looked at the math and, well, basically said the chances of actually seeing it were practically zero.
Huh? Famous last words in science, maybe.
You could say that. Because, well, fast forward to 1979, and bam, they found the first clear case of strong lensing. It was a double image of a quasar. QSO 0957 plus 5/6 to 1.
So it's possible, after all.
Definitely. And that really kicked things off. Since then, hundreds of these systems have been found. Galaxy clusters acting as lenses, creating those amazing stretched out arcs of light from galaxies behind them.
Those are stunning images. You see them sometimes.
Yeah, even those sort of incomplete rings of light, Einstein rings, and some pretty complete ones too, like LRG 3757. It's visible proof that gravity bends light.
Okay, so let's just break down the basic physics. Gravitational lensing, how does it work in simple terms?
Right, so basically anything with mass warps space-time around it. Think of like a heavy ball on a stretched rubber sheet.
Creates a dip.
Exactly, a dip. That's space-time curving. Now, light from a distant object, say a star or galaxy, travels through that curved space-time as it passes by a massive object in the foreground, the lens.
So its path gets bent?
Its path gets bent. And if the source, the lens, and us, the observer, line up just right, almost perfectly aligned.
Which must be rare.
Very rare. But when it happens, the light bending can create multiple images of the background source. Or it can distort the image, stretch it out, make it brighter. It's like looking through a weird cosmic magnifying glass.
A funhouse mirror, maybe?
Yeah, that works too. Now, there's a difference between strong lensing and weak lensing.
Okay.
Strong lensing is what we've been talking about, those dramatic visible effects like multiple images or arcs for individual objects. Weak lensing is much subtler. It's a statistical thing you see over large patches of sky, tiny distortions in the shapes of lots of background galaxies caused by all the matter in between.
Right. Subtle, but maybe tells you about the large-scale structure.
Precisely. And then within strong lensing, you can break it down further. Macro lensing is when you can actually see those separate images or arcs.
Like the quasar example.
Exactly. But then there's microlensing, and that's our focus today.
Okay, microlensing. So what's different there?
With microlensing, the multiple images created are so incredibly close together, angularly speaking, that our telescopes can't separate them. They just look like a single point of light.
So you don't see arcs or multiple dots?
Nope. What you see instead is a change in brightness. Because everything's moving, the source star, the lens star, us on Earth, the alignment changes over time.
Right. Things aren't static up there.
So as the alignment gets better, the background star appears to brighten, and as the alignment gets worse, it fades back down.
How long does that take?
For stars lensing other stars, it can be pretty quick, hours or days, maybe weeks. For something bigger lensing, like a quasar, it could take years.
And the brightening can be significant.
Oh yeah, several magnitudes brighter at the peak. That's a huge increase in apparent brightness.
Wow. And you mentioned complexity, like if the lens isn't just a single star.
Right, if the lensing object is, say, a star with planets, or maybe a binary star system, or even a whole galaxy cluster for some types of lensing, well, that adds complexity. The way the background light brightens and fades the light curve, it gets more complicated. It won't be a simple smooth bump.
You get extra wiggles or spikes in the light curve.
Exactly. And those little deviations can tell you about the structure of the lens itself, like revealing the presence of a planet.
Okay, fascinating. So where did microlensing really get its start as an observational technique? Hear about dark matter searches.
Yeah, that was the big initial push. Back in the 80s and 90s, astronomers were hunting for dark matter, especially in the halos of galaxies.
That stuff we can't see but know is there from gravity.
Right, and one idea was that maybe galaxy halos are full of things called machos, massive compact halo objects. Think dim stars, brown dwarfs, maybe lone black holes or neutron stars.
Things made of normal matter, but just hard to see.
Exactly. So the thinking was if these machos exist in large numbers, they should occasionally pass in front of stars in, say, nearby galaxies like the Magellanic Clouds or even distant quasars.
And cause microlensing events, little brightenings.
Precisely. Look for the temporary brightenings of those background stars or quasars. If you see enough of them, you can estimate how many machos there must be.
Sounds straightforward enough, but I guess it wasn't easy.
Oh, incredibly challenging. These events are super rare for any given star. You need to monitor millions, literally millions of stars night after night for years.
Yeah.
And you need incredible precision to detect the subtle changes. It wasn't really feasible on a large scale until the early 90s.
That's when the big survey started.
Yeah, 1993 saw the launch of major projects like EROS, OGLA, MACHO, DUO, MOA, huge collaborations, dedicated telescopes just staring at dense star fields.
Okay, so they ran these massive surveys. What did they find? Did they find the machos?
Well, they found thousands of microlensing events, which was amazing. It proved the technique worked incredibly well, especially for events within our own galaxy or towards the Magellanic Clouds.
But not the dark matter kind.
The rate of events they found towards the Magellanic Clouds was, well, much lower than expected if machos made up most of the halo dark matter.
Ah, so it sort of ruled out that specific dark matter candidate, or at least a big chunk of it.
It largely excluded the possibility that stellar mass objects like faint stars or black holes, up to a certain mass range, make up a significant fraction of the Milky Way's dark matter halo. A really important negative result, in a way.
Right, knowing what isn't there is also crucial. So, if it wasn't solving dark matter that way, where did microlensing go next?
Well, astronomers quickly realized that while machos might be rare, the technique itself was incredibly sensitive, and it was particularly sensitive to planets.
The exoplanet connection.
Exactly. If the lensing star had a planet orbiting it, that planet could cause its own little gravitational perturbation on the light from the background star.
Like a secondary, smaller lens.
Kind of. It creates those extra bumps or deviations in the main light curve we talked about.
So the focus shifted from dark matter hunting to planet hunting.
Pretty much. The constraints on machos were getting tighter, and the potential for finding planets, especially planets further out from their stars, where other methods struggle, was huge.
When did they find the first one this way?
The first confirmed microlensing exoplanet discovery was announced in 2004. It was a gas giant, about 3 times Jupiter's mass.
Okay, so it worked.
It definitely worked. Then, just 2 years later, 2006, they found one much smaller, closer to Earth's mass, maybe 5 times Earth mass, I think. That was a big deal.
Finding smaller planets is always harder.
Always. And then in 2008, something really cool. They detected a system with 2 planets orbiting the lensing star.
2 planets from one event.
Yes, and because the event lasted a while, they could actually see subtle changes in the light curve that seemed to correspond to the orbital motion of those planets during the event.
That's incredible. Seeing planets orbit another star through these light changes.
It's mind-blowing, really. It shows the power of the technique. By the end of 2020, something like over 100 exoplanets had been found using microlensing.
And it finds different kinds of planets than other methods, right?
Generally, yes. Microlensing is more sensitive to planets at wider orbits, maybe Neptune's distance or further out, and even free-floating planets not orbiting any star. This complements methods like transit or radial velocity, which are better at finding planets close to their stars.
So it helps give us a more complete census of planets out there. You mentioned light curves, like for MOA 2010 BLG 477.
Right, that's a good example. You see the main smooth brightening and fading from the star, but then there are these extra sharp features superimposed on it. That's the signature of the planet.
Like a little blip on the radar.
Exactly. It's like catching a fleeting glimpse of another solar system's structure.
Okay, so microlensing evolved from dark matter searches to a successful planet-finding technique. But the story doesn't end there, right? Enter Gaia.
Right. Just when you think things are settling down, Gaia comes along and completely changes the game again.
How so? What does Gaia bring to the table for microlensing?
Gaia's mission is ultra-precise astrometry, measuring the positions, motions, and distances of billions of stars with unprecedented accuracy.
Okay.
One key thing it measures is proper motion, how stars move across the sky over time.
Their apparent sideways drift.
Exactly. By measuring the proper motion of the foreground lensing star very accurately, Gaia helps us pin down its characteristics much better, its distance, its transverse velocity. That helps us better interpret the lensing event itself.
So better information about the lens helps you understand the whole event better. Makes sense.
Yeah. And another really powerful thing Gaia allows is prediction.
Prediction.
Because Gaia measures positions and motions so well for so many stars, we can essentially fast forward their movements. We can predict when a foreground star is going to pass very, very close to a background star in the future.
You can see potential lensing events coming.
Exactly. We can identify stars on a collision course, well, not a physical collision, but an alignment course. This lets us know years in advance where and when to look for potential microlensing events, both the brightening kind and something
Okay,
else.
what's this something else? This must be the astrometric microlensing part.
This is it, astrometric microlensing. So remember how microlensing creates multiple images, but they're too close to resolve?
Right, they look like 1 point.
Well, even though we see them as one point, the center of that combined light, the photocenter, actually shifts slightly on the sky during the event.
It wobbles. The position wobbles.
Yeah, tiny wobble. As the magnification changes due to the changing alignment, the relative brightness of those unresolved images changes, and that makes the centroid of the light appear to move in a little loop or path on the sky.
Whoa. Okay, how tiny are we talking here?
We are talking incredibly tiny. The maximum shift is typically around 1 milliarc second, maybe a bit more in rare cases.
1 milliarc second. What is that in real terms?
It's minuscule. It's like seeing a human hair from maybe 10 kilometers away, or the width of a coin seen from hundreds of miles away. Utterly impossible to detect from the ground because our atmosphere blurs everything too much.
But Gaia can do it. From space.
Gaia's precision is designed for exactly this kind of measurement. It can measure positions down to microarc seconds for bright stars and certainly milliarc seconds for many.
And what do you gain by measuring this tiny wobble?
This is the really exciting part. Measuring that astrometric shift, that wobble, gives you a much more direct way to measure the mass of the lensing object.
How accurate.
Potentially down to about 1% accuracy for the lens mass in ideal cases. That's phenomenal. People were doing theoretical studies about this possibility even before Gaia launched.
1% mass accuracy for a random star or object out there. Just from a wobble.
It sounds like science fiction, but the physics works out.
Okay, has anyone actually measured this wobble yet?
Yes. Though the very first measurement wasn't actually Gaia, it was Hubble.
Hubble got there first.
Yep. Sahu and colleagues used the Hubble Space Telescope in 2017. They were observing a nearby white dwarf star, Stein 2051b,
A white dwarf. Okay.
and they saw it pass in front of a more distant background star. They measured a tiny shift in the background star's apparent position, about 2 milliarc seconds.
So they saw the wobble.
They saw the wobble, and from that measurement, they calculated the mass of the white dwarf.
What did they get?
About 0.67 times the mass of our sun, with an uncertainty of about 0.05 solar masses.
And that was important.
Hugely important. It was a direct gravitational measurement of a white dwarf's mass, and it matched the theoretical predictions for white dwarfs really well. It helped confirm our understanding of degenerate matter, the weird super dense stuff inside them.
Okay, so Hubble proved the concept. What about Gaia's predictions of these events? Have those started to pay off?
Yes, people started using the Gaia data, especially the second data release, DR2, almost immediately to look for these predicted events.
Like who?
Well, Kluters and collaborators, for instance, back in 2018, they specifically looked for foreground stars with high, proper motion stars, visibly moving quickly across the sky that were predicted to pass close to background stars.
Makes sense. Fast movers are more likely to cause events sooner.
Right. And they calculated the dates, the predicted separations, and crucially, the expected size of that astrometric wobble.
Did they find any good candidates happening soon?
They highlighted a couple that were happening around that time or very soon after. One involved a star called Luton 14323.
Okay.
It was predicted to have its closest pass to a background star in July 2018, with a pretty hefty predicted shift of 1.7 milliarc seconds.
Wow, it's big for these things.
Yeah. And it was predicted to pass near another star later, in March 2021, with a smaller shift, about 0.7 milliarc seconds. Another one they flagged was Ross 322, predicted for August 2018, also with about a 0.7 milliarc second shift.
Were these events actually observable by Gaia? Was it looking in the right place at the right time?
That's the key question. Apparently, the first Luton event wasn't perfectly timed with Gaia's scanning pattern, but the other two, the second Luton pass and the Ross 322 event, were expected to fall within Gaia's observations.
So the data should be in the can, so to speak. We're just waiting for the analysis.
Pretty much. The Gaia data releases are complex and take time, but yeah, we're eagerly awaiting the results for those specific predicted wobbles.
That is cool, like setting a cosmic experiment in motion and waiting for the outcome. Are there other predictions too?
Oh, yes. Mustill and colleagues did a different search, looking for events closer to home within about 100 parsecs that would happen before 2035.
So more nearby events.
Right. They found 7 possibilities, one of which looks particularly promising for early 2030. It involves 2 fairly bright stars, which makes detailed follow-up easier.
And it's not just normal stars doing the lensing, right?
Yeah.
You mentioned white dwarfs before.
Definitely not just normal stars. Bramich did a huge search of the entire Gaia DR2 catalog, 1.7 billion stars, and predicted 76 microlensing events up to 2026. A bunch of those, 9 I think, were predicted to be caused by another white dwarf, LOWD 37, and 5 more by Stein 2051b again.
The same one Hubble saw.
The very same. It shows how these different searches are confirming the importance of certain objects.
Any even weirder lenses predicted?
Well, OFEC looked into the possibility of foreground pulsars acting as lenses.
Neutron stars.
Yep, rapidly spinning neutron stars. Their motion is often well known. He found a couple of candidates where a pulsar might pass in front of a background star, potentially causing an astrometric shift of maybe 10 microarc seconds or more.
Microarc seconds. Even tinier, but maybe detectable.
Still incredibly challenging, but potentially doable with future tech or maybe even current instruments pushed to their limits. It would be an amazing way to study pulsars.
Okay, so we have Gaia doing this amazing space-based astrometry. Are ground-based telescopes still important in this?
Absolutely essential. There's a real synergy. Gaia gives you the precise position and motion information, the astrometry, the wobble, yes. But ground-based surveys, like OGLE, are fantastic at getting very detailed photometry, measuring the brightness changes over time, the light curve.
So you combine the wobble data with the brightening data.
Exactly. Rybicki and colleagues looked at this. They took an old microlensing event found by OGLE, one called OGLE3 Ulan S par R2.
Okay.
And this event is thought to be caused by an isolated black hole.
A lone black hole lensing a star.
That's the likely interpretation.
Yeah.
Now, by itself, the light curve gives you some information, but there are degeneracies. But Rybicki predicted that if you combine the OGLE light curve data with the kind of astrometric information Gaia could provide for such an event.
You could pin down the mass better.
Yes. They estimated that for events like this involving heavier objects, say over 10 times the mass of the sun, and if the background star is bright enough, combining Gaia astrometry and ground-based photometry could let you measure the lens mass, the black hole's mass, with about 10% accuracy.
Measuring a black hole's mass to 10% using a wobble and a flicker of light.
That's the potential. It would be a massive step forward for finding and characterizing these isolated black holes that are otherwise invisible.
Okay, this is really wrapping my head around it. We've gone from seeing light bend in eclipses, this sort of proof of concept,
A huge proof of concept.
to searching for dark matter with machos, which didn't quite pan out as hoped but proved the technique.
Right, showed the sensitivity.
Then finding hundreds of exoplanets in orbits that other methods miss.
You get us a broader view of planetary systems.
And now, with Gaia, measuring these almost impossibly tiny wobbles, the astrometric shifts, to weigh stars, white dwarfs, and potentially even black holes with incredible precision.
It's really been an amazing journey for gravitational lensing, especially microlensing, pushing the boundaries of precision measurement.
It really is. And like you said, it's still happening. These predicted events, the Gaia analysis, we're still waiting on results.
Exactly. We're right in the middle of this next phase. Gaia's future data releases will hopefully contain detections of these predicted astrometric signatures, and likely many more we haven't predicted yet.
It really makes you think, doesn't it? The fact that we can now detect these minuscule movements, these gravitational whispers, it just opens up whole new ways to perceive the universe, to find the hidden mass and the exotic objects out there.
It changes how we see.
Yeah. What else might we uncover as we get better and better at measuring these subtle effects? What other secrets are hidden in these tiny shifts and flickers? It's something profound to consider about how much is still out there, waiting in the subtle details.